Welcome to Hawkins Training for Concrete Fundamentals. This course will cover health and safety, makeup of concrete, concrete properties, volume calculations, site considerations, site preparation, forming concrete, placing concrete, and finishing concrete. Health and safety for working with concrete has many hazards. Dry cement's chemical properties, corrosive, carcinogen, organ toxicity, mixes with moisture in the lungs when inhaled. Constructing and erecting formwork by hand or with equipment. Shoring work on both forms and earth retention. Access and egress into, out of excavations or scaffolding. Slips and trips. Falls, especially walking on mesh or rebar that is not visible, working at heights. Placing concrete, high pressure hoses, pumps, concrete hopper, heavy lifts, and carrying cement bags. Busy traffic and reversing concrete trucks, skid steers, other workers, or bystanders while personnel are using or placing concrete under pressure. Repetitive motions and awkward positions. It can be excessively hot. For all hazards pertaining to concrete work, refer to our internal SWPs and SJPs. Concrete forming and reinforcing bar, SWP, concrete placing and finishing, SWP, concrete hopper, SJP. Always review the safe work practices and safe job procedures prior to beginning work. Health and safety PPE. Personal protective equipment is required for working on any construction site as per the Green Book, Regulation 213/91, Sections 21 to 27. Every worker shall wear the following protective equipment at all times on a project: steel-toed boots, hard hat, high visibility clothing. A worker shall use protection appropriate in the circumstances when there is a risk of injury on a project, for example, safety glasses, gloves, or a mask. 2 companies were fined $400,000 after workplace fatalities. What happened? A section of a building under construction in London, Ontario, collapsed during a 4th floor roof level concrete pour, resulting in the death of 2 workers and 4 additional critical injuries. Why did this happen? More concrete was used than designed due to incorrect measurements, so the weight of the concrete caused the support beams to fall. Inadequate supervision, information, and quality control resulted in these issues going undetected. How could this have been avoided? If proper concrete measuring techniques had been used, with competent supervision and instruction, SWP and SJPs exist to protect everyone and ensure critical steps are not missed. Pause here and view these pictures of the collapse site located in London, Ontario. Concrete failure statistics. A survey sent to civil engineer firms and inspection agencies across Canada, 250 consultants, every federal and provincial department, all municipalities with over 100,000 residents, gave the following results from a 1-year period. 188 reported cases of errors in concrete structures, 29 resulted in collapse, and 118 deteriorated, had excess cracking, spalling, deflection, or settlement. 50%, about half of the cases of failures, were design errors, poor calculations, or incorrect analysis. The other half were construction errors. The leading factor for construction errors and failures is due to poor installation of reinforcing, such as formwork, bracing, and supports. It's concrete, not cement. The composition of concrete is 26% fine aggregate, 42% coarse aggregate, 16% water, 10% cement, 6% entrained air, which varies, and admixture, which varies if needed. Concrete basic components. Cement is an ingredient in concrete. The terms are not interchangeable. An example is Portland cement. Once hydrated, Portland is the paste that binds all the components of concrete together. Cement mixed with water on its own is sometimes referred to as grout, which contains no aggregate. This powder/paste component of concrete is what will burn your skin. Be sure to review the safety data sheets. Portland cement dust is known to be a carcinogen and causes silicosis, a type of lung disease. Why does concrete need air? When temperatures reach freezing levels, the moisture in the concrete needs somewhere to expand to. The millions of air bubbles within the concrete allow for the expansion during freezing without cracking the concrete from the inside out. For exterior flat work like parking lots, driveways, pool decks, patios, which are subject to freezing and thaw cycles, an air content of 4% to 7% of the concrete volume is used. For underground or climate-controlled applications, the air entrainment is not critical. Air entrainment increases the workability, reduces bleed water, and reduces strength of the concrete as well. Air content is often tested on site and is set by the batching plant. Make sure your concrete is tested at the start of your pour so you can catch a failed test early. Additives or admixtures. Admixtures are formulated chemical components that are used to modify certain properties of concrete. Admixtures are the material other than cement, water, and aggregates. Some examples are accelerators for cold weather to speed setup of strength to resist frost. Calcium chloride, when used as an accelerator, should not be used in reinforced concrete because it causes rust in the rebar. Also causes a darker color to the concrete and can be blotchy. Retardants for hot weather and when applying special finishes, also for small crews. Plasticizers or superplasticizers increase workability without increasing slump. Air entrainment does the same, decreasing strength, but are expensive and only last 30 to 45 minutes. Colors, you purchase, your responsibility, either mixed in or powdered on top. Heat, used from November 1st to April 15. Ice, for hot summer months. And fiber mesh for reinforcement. Cement-based mixtures. While the below are not all traditional concrete, they are examples of common cement-based mixtures. Permeable concrete allows water to pass through to improve drainage. Coarse aggregate, little to no fine aggregates, cement and water. Used in garden planters, parking lots, stormwater management, etc. Distinctive voids when dried, low MPa. Mortar, type N, S, M, etc. Smooth application used for parging, surface repairs, aesthetic, masonry, bricklaying. No coarse aggregate, fine aggregate, sand, limestone, and water for applying thin layers. Non-shrink grout. As the name implies, it doesn't shrink. Contains specific admixtures to reduce shrinking, cement, sand, water, and sometimes fine aggregates. Used for filling gaps and ensuring stability under load-bearing elements, masonry columns, anchoring bolts, etc. This has a high strength. U-fill or unshrinkable fill, also called flowable fill, very viscous, flows and spreads easily, not the same as non-shrink despite the name, used as a self-compacting, non-structural backfill or trench fill, utility trenches, abandoned pipes, etc. Contains cement, fly ash, water, and fine aggregates with low strength. Compressive strength. Compressive strength is measured in MPa or PSI, pressure ratings. 1 MPa equals 145 PSI. Concrete strength increases with time until it reaches 100% design strength. This is called curing. Typically, this is 28 MPa, 30 MPa, or 32 MPa. Check the details and specifications on the drawings to know what you need for the project. Compressive strength is often a testing requirement to verify the quality of the concrete. Concrete samples are taken and placed into cylinder molds where they will later break them in a lab while measuring the force, MPa, it takes to break. See the attached chart below with showing the number of days needed to meet strength. Here are some applications of various strengths. 1 to 14 MPa is typical for fill concrete or non-shrink fill. 20 MPa typical for things like fence posts. 25 MPa is typical for curbs. 30 MPa good for most exposed slabs. 32 MPa used for colored concrete, good for almost anything. And 55 MPa is typical for unit paving. Factors that affect strength: water to cement ratio, air percentage, sand to gravel ratio, additives, temperature, humidity, quality of materials, curing environment. These all impact concrete. Slump. Slump is the measure of the concrete's consistency and workability and needs to be indicated when ordering. The less slump, the stronger the concrete is, but the harder it is to work with. Typical slump is from 2 inches to 6 inches. 3 inches to 4 inches is standard. 6 inches is for fill. Unit pavers are made with no slump. Ordering concrete. From a ready-mix concrete truck, it's pre-mixed concrete from the plant, made according to a design mix. Will be tested on site to confirm actuals match the design. For structural applications, large consistent quantities, when strict adherence to design is needed and cannot be altered on site. Ordering from a volumetric truck can adjust the concrete mix on site to vary required slumps. Best for smaller projects when lower volumes are needed. Hand mixing concrete, buying a few bags of cement and aggregates and mixing with water on site by hand or with a mixer. Best for very small quantities or with limited access areas when parging or patching existing concrete. More on ready-mix concrete. There's usually a minimum order, 3 cubic meters to 4 cubic meters. Concrete is measured in cubic meters. What time do you want your concrete? Concrete that will be tested needs to be poured no more than 2 hours from batch time or it will not be accepted. What time spacing do you want trucks to come at? How are you getting the concrete to where you need it? What size aggregate is specified on your mix design? What slump do you need? Remember, you can always add some water on site, but the slump must fall within your mix design. What percentage air is specified on your mix design? All of these items must be considered when ordering ready mix. Along with these additional ones, do you require any admixtures? Do you require a belt truck, a concrete pump? These require extra notice to book. Call your order in 48 hours prior to pouring to ensure delivery at time needed. Confirm order closer to scheduled time, and concrete must be tested on site before pouring. All measurements need to be the same unit of measurement when calculating the volume for concrete. For example, our slab is measured in inches and feet, but we order concrete in cubic meters. Ensure they are the same unit of measurement. Please review this here, pause the video, take a screenshot, and store it for later, as it can be a very complicated process, but understanding this is key to ordering concrete correctly. When purchasing bagged concrete, there are a few things to consider. When buying concrete to hand mix, a quick rule of thumb is 1 skid of 30 kilogram bags is about 1 cubic meter of concrete. Always double check with the supplier. There are many online resources that can help calculate how many bags you need for your project. When in doubt, get a second opinion. If you think you're going to order too much or too little, double check with your supervisor or with the supplier. Forming concrete. For a concrete pad, first install a base. Review the public and private locates. Excavate to undisturbed soil. No organic matter to a 6-inch depth and with a 6-inch apron. That is a 6-inch in addition to the width and length of the finished product. Base gravel is added and compacted. Check the project details on the drawings to determine the type and depth needed. Check if insulation or filter cloth is required. Testing of the subgrade and granular must be completed prior to ordering concrete. Here are concrete formwork definitions. False work. Structural supports and bracing that is used to support all or part of the form until the concrete is poured. Flying formwork. A formwork system designed to be hoisted between various levels as a unit. Gang forms. Large panels designed to be hoisted as a unit, meant to be reused. Knockdown forms are traditional forms, typically single-use. Panels. Sections of form intended to be connected together. Sheathing. The material directly being supported by wales. Concrete is placed against it, the actual form part or shell. Wales, horizontal shoring placed against sheathing to directly resist pressure from the sheathing, which is the horizontal bracing. Struts, vertical shoring placed against the wales. Usually, forms are made of spruce wood, can use cheap grades of wood, but materials must be picked out for straightness and where appearance isn't critical. For footings. Warped forms may need additional stakes or reinforcement to maintain shape. Metal and plastic forms available in varying sizes, 4 inches, 6 inches, etc. Easy to use by staking into place, but expensive to purchase. Can cut hard earth for rough forms if cuts are straight and not tapered out because of frost heaving. Already existing building and concrete in which you would have to dowel or put expansion joint to form against. For exposed concrete, form ply will give best finish. Hides wood grain but more expensive. The procedure. First, number 1, layout. Know your tolerances and use appropriate methods. 2, stakes. When in doubt, add additional reinforcing. 3, establish grades. 4, form to stakes. 5, double check measurements, grades, and slope. Forming slabs. Determine the thickness of the slab. A 4-inch thick slab typically uses 2x4 lumber. Actual measurement is 3.5 inches. A 6-inch thick slab for anything that will be driven on, driveway, parking lot, uses 2x6 lumber with an actual measurement of 5.5 inches. When forming curves, foundation walls sometimes require Perry or Doka forming. Slow curves over a 4-foot radius can be done with 3/4 inch wood or aspenite ripped in strips. The wood will curve easier if it is wet. Another option is to buy flex board, which is plywood with grooves cut into the surface, but can be costly. Sharper curves can be done with a 1/4 inch masonite cut into strips and stakes placed every foot. Masonite can be doubled or tripled for strength. Stakes are used to keep forming in place. 2x2 by 24 inches long is standard. In less stable soil, use a 2x4 stake. Best cut off after forming, but can't be used again, but depends on the method of striking off. Form must be solid, reinforce corners with blocking, stake frequently, and nail every stake. Sometimes stakes need to be braced. Consider the head pressure. Steel curb pins can also be used as an alternative to wood. Fasteners that can be used for forming include straight nails are most common and work best. Do not use spiral or galvanized. Double-headed nails make pulling them out easy but are more costly. Nail guns can be used as they don't disturb the stakes but are not commonly used in landscape construction. Construction screw set with an impact driver work in 3/4 inch wood or masonite. Regular screws do not penetrate masonite effectively. Use snap ties to brace form to form and stay embedded in the concrete. Insulated concrete forms, or ICFs. ICF are less common but still are an effective way to form concrete. Used mainly in residential applications for buried foundations, more expensive but quicker and easier to install. Allows concrete to cure stronger due to the insulation of the blocks. Pre-made blocks are customizable and can be fit together like Lego with rebar chairs built in. Requires different bracing and supports than typical wood forms. Forms don't need to be stripped. R value or insulation factor can be as high as R50. A fun fact, the largest ICF project was in Utah, a 206,000 square foot megaplex theater that used over 35,000 ICF blocks. Concrete structures. The Three Gorges Dam on the Yangtze River in China is the heaviest concrete structure in the world. The dam is said to contain 144,309,356,753.51 pounds of concrete. When we convert this into cubic meters, that equals 27,276,383 cubic meters of concrete that was used. Roughly, just over 3 million ready-mix trucks. The dam is so large, it slowed the rotation of the Earth. The dam is 2,335 meters long and 185 meters tall. It is 115 meters thick at the base and 40 meters thick at the top. Pause the video if you'd like to review these pictures in detail. This is a pour for the foundation of the tallest building in San Francisco. It took 18 hours to complete. The slab is 14 feet thick and nearly an acre. Things to consider when getting ready to have concrete poured. What is the site access? How close can we get the truck to where we need it? Will ferrying concrete cause more damage than the cost of a pump? Consider how close you can safely get a machine to the formwork, and will that machine have the reach and lifting capacity necessary to place the concrete? How long will it take to place the concrete you need with the machines available? You may need to split an order into 2 or more trucks if it is going to take too long to place before it kicks. Be mindful that a pour that takes a long time can result in differentials in temperatures, and this can cause your concrete to move, even if it has already been screed off. Do not let the concrete truck leave until you are sure that you're done and all tools and equipment have been washed or you have water on site. The water on the truck belongs to you. Use the resources as they are available. Spotter signals when pouring concrete. Learn these 11 hand signals to communicate effectively with the driver. Pause this video, take a screenshot so you can review these in the future. Working with and pouring concrete in cold weather concrete conditions are found when the air temp is 5 degrees or below, or when the temp may fall below 5 degrees within 24 hours of placing. The challenges: concrete that is allowed to freeze while it is plastic state can have its potential strength reduced by more than 50%, and its durability properties will be dramatically reduced. The solutions are: concrete can be insulated after pouring with special insulating tarps, but regular tarps will work fine covered with straw for colder times. Form removal can be delayed to protect, but removal is more difficult. Heaters: burning fossil fuels can't be used because carbon dioxide buildup will cause dusting. Problem with all coverings can cause discoloration of the finished surface. Pouring concrete in hot weather. Hot weather concreting consists of temperatures above 20 degrees, low relative humidity, high wind speeds, and solar radiation or heat gain. The challenges: increased water demand, accelerated concrete slump loss, increased rate of setting, increased tendency for plastic shrinkage cracking, increased concrete temp resulting in lower ultimate strength, increased potential for thermal cracking. The solutions: place and finish at night or early morning. Erect sunshades or windbreaks. Apply evaporation retarders. Use of fog sprays. Cover the concrete with moisture, retaining coverings such as wet burlap between finishing operations. Be sure to consider overall efficiency and cost for pouring concrete. For example, here's a comparison of a pump truck versus labor and skid steer for 50 cubic meters of concrete. The pump truck total is $1,100, whereas the skid steer and labor is $1,800. This is an important consideration. We automatically think that labor and skid steer would be cheaper, but because the pump truck works so much quicker, it is actually more economical. Take a screenshot and use for future reference. Let's consider slope when pouring concrete. All slabs need some drainage. Slope depends on the usage and the texture. Creating slope sets the amount of drainage on a slab. Slope percentage equals rise or run times 100. A 1% slope equals 1 centimeter every meter. Some electrical pads require a total level surface with 0% slope. Flagstone and interlock surfaces require a 2% slope. Concrete can have a 1% slope if it has a smooth finish. A very smooth finish can have 0.5%. This would be for indoor use. Maximum slope for a walking area is 4%. Maximum slope for a wheelchair ramp or driveway is 10%. Be sure to set the forms to the grade that you want to avoid hand grading. Contraction. Concrete will move with the frost, expand in hot weather, contract with age, creating stress greater than the strength of the concrete. The joint is used where a slab meets a building or a fixed object, that is, a column, post, or other slab like a garage floor. Joints are a 1/4 inch below the finished surface to allow room for joint sealing compound like butyl caulking or polymeric sand. Joints are also used to control where the concrete will crack. Can be formed into the job with fiber or wood strips, tooled into the wet surface with a jointing tool, cut into the surface with a concrete saw before fully cured. Must be 1/4 of the depth of the slab. Should be used in a grid of no more than 25 times thickness of slab. So for a 4-inch slab, 25 times 4 inches equals 100 inches, or approximately every 8 feet. Can be more when larger aggregate is used, less slump, or thicker concrete. The length of each section should be no more than 1.5 times the width of the section. Should follow a pattern for aesthetic purposes and to avoid creating small section which will break off. Reinforcement for a joint should extend through the control joint. When jointing under flagstone or brick, place the joints where they will be under the finished surface. Use a straight edge when scoring a control joint, such as a 2x4 piece of lumber. Reinforcements are used to hold the cracks in the concrete together when it does crack. It does not add strength to the slab. It is not recommended if there is a good base under the slab. Options include fiberglass mesh is the easiest and is added to the mix on site. Only intended for shrinkage cracking, and will not stop a crack from spreading. 6x6 inch mesh purchased in 4x8 sheets. 3/8 inch or 1/2 inch rebar wired together at 24 inches on center. Overlaps must be wired together with at least 18-inch overlap. Every joint must be wired together and leave in 3 inches from the edges. Once tied, the cage should not rattle when shaken, and the bars should be tight together. Epoxy-coated rebar costs more and is only necessary when the slab is exposed to de-icing salt. There are several ways to hold a reinforced grid in place. Set up saddles, bricks, or bits of broken concrete, but it makes it difficult to wheelbarrow the concrete into place. Pull the reinforcing into place after the concrete is poured while leveling and consolidating, but this can be hard to get it in the right place. For small areas, best to pour from the top. Rebar sits on spacers called chairs to keep the rebar properly encased in the center of the concrete. Grade stakes are crucial for pouring concrete as they act as physical guides to set the exact height or grade and level of the slab or footing, ensuring it's not too high or too low and is perfectly flat or sloped as intended, using tools like laser levels to mark the desired elevation on the stakes for screeding concrete over them. They support forms, define the finished surface, and eliminate guesswork, making the process accurate and efficient for patios, driveways, and foundations. Essential for large areas, can use rebar or spikes with tops painted to reduce tripping hazards. Hammer down as you finish the concrete. Concrete finishing is the process of shaping, smoothing, and treating freshly placed concrete to achieve the desired surface appearance, durability, and performance. It begins immediately after placement once excess bleed water has evaporated and involves a sequence of techniques such as screeding, floating, troweling, edging, and jointing. These steps ensure the concrete is level, properly compacted, and free of surface defects. Depending on the project requirements, finishing may produce a range of textures and aesthetics, from smooth, steel-troweled floors to broomed, exposed aggregate, or decorative stamped surfaces. Proper timing, tools, and environmental control, temperature, wind, and moisture, are critical to prevent cracking, scaling, or surface weakness. Finishing the concrete, spading and striking off. As the concrete is placed, it should be roughly level to get the right quantity in place. You don't want to have to shovel a lot later. Best if one person can direct placement independent of finishing, but depends on the size of the job. Consolidation or vibration, used to remove air pockets or getting the concrete to fill in all the voids. Use a mechanical vibrator for walls, but not for slabs, to avoid separation of the aggregate. Edge of slabs and step risers can be tapped with a hammer to eliminate air pockets. A palm sander also works. The finishing should be done 1 to 3 days after pouring. Be careful not to chip or crack the concrete. If the form's installed properly, there shouldn't be a problem. Cleaning solutions available to clean discolored surfaces, but only if necessary because they can weaken the surface if not used correctly and can cause their own discoloration. Read the directions before using. Concrete forms should be stored away in an organized manner for reuse. Remove nails, stack neatly, etc. Throw away what cannot be reused. Joints need to be cut in the day after the pour. Better to use a carborundum blade, not a diamond blade, as the loose aggregate will pull the diamonds out of the blade. Chalk line for pattern, and best done using straightforward as a guide. Make sure the concrete is set up enough that the aggregate is not ripping out, but if you wait too long, it will be too hard. Use water when cutting, a wet saw method, when possible, to reduce dust hazard. Curing maintains adequate moisture and temperature so the concrete can develop strength and durability. It creates a permanent chemical bond, locking the aggregate into place. The water in the concrete gets used in the chemical reaction. It doesn't evaporate. Bleeding refers to water rising to the surface as the concrete settles. This usually means there is too much water or insufficient fines to retain the water. In about 3 days, concrete reaches half of its strength. In 28 days, it reaches full strength, the MPa of the concrete. As long as water is present, concrete will continue to gain strength as the hydration continues. Several methods can be used to retain water. Heat causes water to evaporate and cold breaks the chemical bonds before they are strong enough. Use one of the following methods as needed: spraying with a hose, soaker hose, ponding, covering with poly, tarping using burlap, waterproof paper, or wax or latex emulsion. Concrete deficiencies and failures. Lots of things can lead to concrete failing, either during the pour during the curing process or after curing as a deficiency. Below are some common types of fails. Form blowout. This happens when the pressure of the concrete exceeds the strength of the forms, causing them to blow out and concrete to spill during a pour. Cracking. Caused by uneven settling before hardening, poor foundation preparation, excessive loads, no control joints, temperature differences, etc. Spalling. The surface of the concrete flakes off or chunks break off. Water can freeze in voids under the surface or voids around rebar. Bleeding. Too much water is added to the mixture or not enough fines to absorb the water so it rises to the surface and creates a weak top layer. Segregation. The aggregate materials and cement mix separate due to too much water, incorrect aggregate sizes, or over vibrations. Dusting. The surface of the concrete produces a fine dust when rubbed instead of hardening solid. It's caused by premature finishing while the concrete is still curing. Collapse. The structure fails entirely and falls apart and can be caused by many different reasons. Here's the summary of what we have learned today. Working with concrete presents many challenges and potential hazards. Never rush a concrete job since you don't get a do-over. Once it hardens, it's set in stone. Be sure of your measurements, quantities, and materials. Double check your layout and grades. Triple check your supports and bracing. Refer to the safe work practices and safe job procedures or consult a supervisor when in doubt. Check the IHSA Safety Manual Concrete Resource, Chapter 42 under Formwork. Thank you for watching today.